Good afternoon, everyone. Thank you so much for being here. Let's imagine a very common scenario that you're sitting in a coffee shop and you're doing your work with your laptop. You could be writing some code, you could be working on a video, anything. And for the most part, your laptop is completely fine for that task. But sometimes you have to do something that takes far more resources that is available in your laptop. Let me give you some examples. On a single-core laptop, compiling Google Chrome takes 16 hours. Running unit tests for libvpx takes an hour and a half. Encoding a 15-minute-long 4K video takes more than 7 hours. And rendering a single frame of Monsters University animation takes 29 hours. One thing that is common between these tasks is that they are occasional. It's not like that you want to compile something every second of every day. You know, like 99% of the time, you're doing a task that your laptop is completely fine for that. But for that 1% of the time that you want to do these time-consuming tasks, it would be awesome if you could immediately borrow 10,000 cores in the cloud, outsource your task, have it done in minutes rather than hours, and then pull back the results, give back the cores, and return to your normal workflow. So many others actually share this dream with us. But for reasons such as limited speedups, high costs, and the limited scope of these programs, this dream is not quite a reality yet. So today, I'm going to talk about this project that we've been working on, GG, which is a framework and a toolkit that makes it practical to outsource everyday applications, such as software compilation, unit testing, 3D rendering, video encoding, to run with thousands-way parallelism on cloud function services like AWS Lambda. OK, let's talk about the challenges that we have in outsourcing programs to the cloud. The first challenge is managing software dependencies. You know, when we are talking about running something on a cluster of 10,000 nodes, we think of frameworks like Spark and Hadoop. But why aren't we using them to outsource our tasks? The reason is that these frameworks, they do not manage software dependencies. It means that if you want to run the compiler or interact with a video encoder or run TensorFlow or any external software, you have to go and get a warm cluster, preload all those programs, and then the framework can run and interact with those programs. But our tasks are occasional. You know, I want to compile something maybe once an hour. So warm clusters could be actually very expensive for these kind of jobs. Like getting 10,000 cores on EC2 can cost you $400 per hour. So we need a way to be able to efficiently pack up a computation that you would normally run on your laptop and ship that to be executed in the cloud in an environment that is different from your laptop's environment. So we need something like a Docker container. But when we are talking about running like thousands of these containers in the cloud at the same time, Docker containers could be a little bit heavyweight. So our solution to this is lightweight containers, which we call it a thunk. And it's basically, it can be seen as a very light Docker file. You know, it's a description of an executable, all of its arguments, its environment, and all of the input data that it needs to carry out the operation. And every piece of data that we have in these thunks is named by the hash of its content. Let me give you an example. So here we have a thunk that we use for pre-process a C file. So it has three parts. The first part is the function, you know, the hash of the binary that we want to execute, the hash of the compiler, the command line arguments that we need to do that pre-processing operation, and the environment variables that are necessary. It also lists every object that is necessary to do this. For example, the compiler itself, the input file, and all of the header files that are included in that C file so we can do the preprocessor operation. And it also lists the output files that it creates. So this thunk has the full functional footprint of the operation that we want to do. And I can ship that and execute that on EC2 or AWS Lambda or my local machine or my friend's laptop. So OK, our solution for managing software dependencies is using these lightweight containers or thunks. The second problem that we have in outsourcing is the round trips that we have to the cloud. You're sitting in a coffee shop with a bad Wi-Fi. Your latency to the cloud is huge. So you want to minimize the communication that you have between the cloud and your laptop. We currently have a lot of systems that we use for outsourcing jobs. Like DistCC and IceCC are two very popular programs for outsourcing compilation. And there are tools like UCOP that can be used to outsource CPU-intensive applications to the cloud. But these programs, they perform best over fast networks. And the reason is that they still keep the laptop in the driver's seat. You outsource your job, but there is still a lot of communication going on between the cloud and your laptop. What we would ideally want is to take laptop out of the loop and have all the communication and dispatching happen purely within the cloud and just fetch back the final results of the operation. So in the previous challenge, I talked about these containers that we can use to pack up individual tasks and offload them to the cloud. Like if you want to compile 1,000 files, you create 1,000 containers for compiling each file, and then you can offload them to the cloud. But here, we need something more. We don't only want to describe these small pieces of tasks, but also we want to be able to describe the whole computation. And our solution to that is linked containers. As I told you, every piece of data in thunks, they are named by the hash of their content. That's also true about the thunk itself. The thunk also has a hash. So whenever in another container, I need the output of this thunk, I can just refer to that by using this hash. The thunk is not executed yet. I don't have its output yet. But I can refer to that using the thunk's hash. So for example, if a later stage, like a compile stage, needs the output of the preprocessor stage, it can name that output. It can refer to that output by using the hash of the preprocessor thunk. Now, if I want to offload this operation to the cloud, what I do is that I send both of these thunks to the cloud. I will execute the preprocessor stage. Then within the cloud, I will send its output to the other container, which does the compile operation, and then I do the compile and fetch back the final result. This is what we call GG intermediate representation, a collection of thunks that are chained together using these hashes. So with this simple construct, you can actually build more complicated graphs. Like this is a representation of GGIR for compiling GNU Hello program. And also, you can build dynamic graphs and things like loops and recursions, and you can even implement combinators like Y Combinator with GGIR. OK, so our solution for managing software dependencies is lightweight containers. A way to describe the whole job and offload the whole job to avoid unnecessary round trips to the laptop is by using linked containers, which we call GG intermediate representation or GGIR. And now the question is that how do we want to get 10,000 cores? How can we do that? We talked about this. The dream is to rent a supercomputer by the second whenever we need that. And warm clusters are expensive because our tasks are occasional. And cold clusters are slow to start. They take a few minutes at least to start. That defeats the whole purpose. But using cloud function services or serverless platforms, for example, on AWS Lambda, you can get 10,000 workers in just a few seconds. And if you run each for like 10 seconds, you're only going to pay $5. That's over 1 day of CPU time just for $5. And there are some projects that actually use this to achieve interactive speeds, like Xcamera, Pyron, and Sprocket. But using cloud functions is challenging. It's not a normal 10,000 core supercomputer. So this is not really about pushing the boundaries of computer science. It's more about the mechanistic improvements that we made to the way that these cloud functions are used. And I'm going to tell you about a few of them. So we made sure that GG runs fast, reliably, and efficiently. For example, we made a lot of effort into our startup time, and GG has faster startup than the other systems that were built on top of these cloud function services. Also, about getting the data from your laptop to the cloud, like your source files or any other thing that you need to offload, by using techniques like HTTP pipelining and multi-threading, we actually managed to outperform AWS's official utilities. And there is also this debate about how do we want to exchange data between these workers. You know, what other applications usually did is that one worker dumps its output to S3, and the other one grabs that output from S3. And that adds a lot of latency. But it was believed for a long time that the Lambdas, they are not allowed to talk to each other. But we found out that using off-the-shelf NAT traversal techniques, the Lambdas can actually talk to each other. And of course, this is our current work, but we see speeds up to 600 megabits per second. And this can actually enable a lot of latency-sensitive applications to be executed on top of these cloud function platforms. Moving on. So our solution for managing software dependencies is lightweight containers or thongs. To reduce the round trips to the cloud, we have a way to describe the whole job and offload that in one shot to the cloud, the linked containers or GGIR. And we spend a lot of time just to make sure that this actually works well. OK, I'm going to talk about one application today, and you can read about the rest of the applications that we ported to GG in our paper. Software compilation. You know, people have spent a lot of time using tools like Make, CMake, and Ninja, and they created these complicated build systems for their projects. And we can't really go and ask, like, can you please describe your build system in terms of GG thongs so I can build it faster? It's not really possible. So we need to automatically infer GG thongs from an existing build system. And our solution to that is a technique that we call model substitution. And the idea is kind of simple. We run the original build system, whatever that is, Make, Ninja, anything. But we replace the build stages, like the compiler or preprocess or the linker, with these model programs. The programs that understand the behavior of their substitutions, but instead of actually running that task, they produce thongs that can be executed later on the cloud. Let me actually show you how it works in action. So here, I want to build FFmpeg on AWS Lambda. And I have the source code here. I'm going to run gg init command. It just initializes gg for the current project, nothing special. If I want to build this program on my local machine, on my laptop, I would run make-j and the number of processes that I have to run that with 4 or 8-way parallelism. But now I want to actually get this thunk abstraction out of this project so I can outsource that to the cloud. So what I would do is that I just prepend my normal build command with gg infer. It does that model substitution that I just told you about. And as you can see, it will be done pretty quickly. Come on. Because it didn't do any useful work. It just created thunks. It didn't actually compile anything. And when you look at the directory, you see that, oh, the build targets are there. Like ffmpeg is there and ffprobe is there. So what's happening? When you look at the content, you see that the content is just a hash. It tells you that if you want my actual output, go and execute that thunk, and it will give you my actual output. And we can actually look at that thunk using gg describe utility, tijbo. OK, let me. So for example, here it says that if you want my output, run the strip utility on ffmpeg_g file. And if I scroll down, I see that ffmpeg_g is also a thunk itself. So I have to go and recursively execute that thunk first and feed its output to this thunk. OK. Now, if I want to actually execute this on Lambda, I can say that gg, please force ffmpeg for me. I want to run this with 2000-way parallelism on AWS Lambda. Let me just make sure that everything is going to fit on the screen. OK. So the first thing that is going to happen is that the program is going to upload all of the files that I need for executing this task in the cloud in one shot. And it happens in just 6 seconds. I uploaded 100 megabytes of dependencies. And as you can see, in just a few seconds, by spending 30 cents, I compiled over 1,800 files. And now we get to the final stages of the build where we have like the link step and the strip. And now it only downloads back the build target, nothing else, no other intermediate data. And I can run FFmpeg as if it was built on my local laptop. Thank you. So we found out that for medium-sized and large-sized packages, GG can actually improve the speed of compilation by 2 to 5x compared to ice cream outsourcing to a warm cluster. And one interesting thing about ICC is that its performance doesn't really improve as you increase the number of cores after some point, because your laptop becomes the bottleneck. And ICC can build Inkscape in 7 minutes. GG does that on AWS Lambda in 1.5 minutes without requiring a warm cluster, and it does that with 50 cents per run, much, much cheaper than maintaining a cluster of 400 nodes. So GG can compile Google Chrome on AWS Lambda in 18 minutes. You can run unit tests for libvpx in just 4 minutes. You can encode a 15-minute-long 4K video in 2.5 minutes, and rendering a single frame of Monsters University animation, that's our current project. We are about to find out. So GG is a framework and a toolkit that makes it practical to outsource everyday applications to run with thousands-way parallelism on Cloud Function services, such as AWS Lambda and Google Cloud Functions. And you know, the next time that you see your friend slacking off at work saying that, oh, I'm waiting for my code to compile, you know what to tell them. Thank you.
Thank you. We have time for a couple of questions.
Hey, hi. Great talk and a great demo.
Thank you.
I had a question on your cost estimation. So is that only the Lambda run cost, or are you also looking at egress charges from AWS back, and then access to S3 and storage of data in S3?
The costs that I had in the table, they are only the cost of executing the Lambdas. The cost of S3 is not in the...
I understand, right? But to be fair, I think you should start even counting that, right? Because that's what the customer is going to pay at the end of the day.
I think that's a fair statement, but I believe that the cost of like storing like 100 megabytes on S3 or storing this intermediate data for just a few seconds or minutes that these jobs are running, I think the cost of Lambda is actually dominating the cost of the whole job.
Fair enough, but egress is going to start biting you in the end because it's like 4 cents for a gigabyte.
In bigger jobs, it could, yeah.
And the other question I had was, maybe I misunderstood this, but you made a claim that GG transfers data faster to S3 than AWS CLI using multi-threading. So can you tell me the difference? Because AWS CLI also has multi-threading, right? So what different are you doing that makes it go faster?
I think the reason that it's faster is actually the fact that we are using HTTP pipelining. So we open one TCP connection to AWS Lambda, and we basically put like 100 requests to upload files at the same time. Thank you.
Hi. So first of all, yes, great talk.
Thank you.
One
Thank you very much.
One of the best I've seen. I have a question. If I wanted to add some new application, for example, you support now unit testing and build, and I want to add something new, bizarre of my own, what would be the effort required? Is it something that anyone can do, or is it like, I don't know, years of work?
Thank you. I think that's a very important question. So I think the question actually has two parts. The first part is that you have to first know if you have 1,000 cores, how do you want to use them? Like in some applications, we don't even know what to do if we have 1,000 cores. We might not actually have a way to speed them up, even if we have 1,000 core on my local laptop. And the second part is that, so currently, GG is not really transparent to the system. We have to explicitly write these things and basically describe our whole dependency graph. So the effort that is required, I think, first is we have to write the programs that do these small tasks, and then the programmer has to spend some time creating these thongs and describing the dependency graph for their program. But of course, what we built, for example, for software compilation, it's just a drop-in replacement. You don't have to make any changes to your project. But for other things, I think there could be a lot of effort to figuring out how do we want to use these threads and what should be our tasks and how should we design our dependency graph.
Okay, thank you. And one more question. You mentioned the Docker containers. Did you compare your solution to using Docker containers?
Actually, we did. I have some results here. So,
Sorry, my bad, I missed that.
Here, we actually ran this job. It's 1,000 workers, each sleeping for 2 seconds. So this job has to be done in 2 seconds, ideally. And we ran it on Google Kubernetes Engine using Docker containers, and it took 3 minutes and 8 seconds. So it seems that the process of starting Docker containers and transferring the images could dominate the task.
Thank you.
Thank you very much.
Thank you very much. Let's thank the speaker again.